Hello everyone, welcome to the Maths Club. So far we found out the volume of the solid generated when a bounded region rotated about coordinate axis. But today we are going to find out the volume of solid generated by rotating a bounded region about a line which is parallel to the axis, and in the first case we will take parallel to the x-axis. So we'll start with an example. This is the example we have. We have to find volume of solid generated by rotating a region bounded by curve y is equal to e to the power x and lines y is equal to 1 and x equal to 2, and this bounded region is rotated about the line x is equal to 3. So first you have to identify this bounded region. So we need point of intersections between the lines and the curves. So here first the point of intersection. First we are going to take this two, y is equal to e to the power x and y is equal to 1. So if we substitute y is equal to 1 in this y is equal to e to the power x, we are going to get e to the power x is equal to 1. And the 1 can be written as e to the power 0. So finally we can conclude x is equal to 0. This is for the first pair. Now if we consider the second pair, that is y is equal to e to the power x and x is equal to 2. So if we substitute x equal to 2 into y is equal to e to the power x, then we are going to get y is equal to e squared. So we have two pairs of values. One pair gives us 1, 0 and second pair gives us 2, e squared. So finally we can say our point of intersections between the curves and the lines are point A, that is 0, 1, and point B, that is 2, e squared. And of course between these two lines, y is equal to 1 and x equal to 2, we have 2, 1. So first we are going to draw the graph of the region bounded. Start with y-axis and x-axis, and we are going to draw the line y is equal to 1, which is parallel to the x-axis, and now x is equal to 2, which will be parallel to the y-axis. So this is the point of intersection between two lines at x is equal to 2 and y is equal to 1. We can consider this point as 2, 1. So here we are going to draw the curve y is equal to e to the power x. This red curve is denoting y is equal to e to the power x, and the point of intersections of this curve with both the lines are a, that is 0, 1, and with the line x equal to 2, it will be b, that is 2, e squared. And this is the region bounded by the curves and the lines. Let's shade this region. So now this bounded region we are going to rotate about the line x is equal to 3, which is again parallel to the y-axis. So this is the line x is equal to 3, and we are going to rotate this region, bounded region, about this line x equal to 3. Whenever any region rotated about a line, and we have seen before also, to generate the solid we need to draw the image of this region about that line of rotation. So here we need to find out the image of the bounded line, that is x is equal to 2, y is equal to 1 and y is equal to e to the power x about this axis of rotation, that is the green line. Y is equal to 1, the image will just be extended part of this line. So this portions also gives the image of this y is equal to 1. And for the image of the x is equal to 2, we have to take another vertical line at a same distance like x is equal to 2 from the axis of rotations. And now for the image of the curve, we'll get this red curve which is symmetric like y is equal to e to the power x about this line, the axis of rotation. Now to complete the solids, we have to draw two circles at both ends of the solids. So if we draw a circle at this end, the top end, and also we need to draw the circle at the bottom end. If we look properly, you will find out there are two parts in the bottom end. This is the first part, which is bounding the image of x is equal to 2 and original x equal to 1, and the second is this vertex, which will go from this point to this point. Now like before, as we are going to use the disk method, so we have to take the cross section of the solid perpendicular to the axis of rotation. So axis of rotation, we have this x is equal to 3. So if we take cross section perpendicular to this x equal to 3, again this will going to form a disk. So to get the disk, we have to again draw two circles which will be perpendicular to this axis of rotation. This is the first circle and this is the second circle. The cross-sectional disk will going to lie between these two circles. And to find out the volume of the entire solid, first you have to find out the volume of this cross-sectional disk, and after that we have to integrate it from the top to bottom, that is from this point to this point. Let's first take a better picture to visualize the solid properly, and then we'll move on to find out the volume of the disk so generated. So this is the picture of the solid so formed with all shaded portion. This representing the cross-sectional disk. Here this is the height or width of the disk as it is parallel to the y-axis, so you can take the width as delta y. This small r representing the inner radius of the disk. From the figure you can say, as this is the line x equal to 3 and this is the line x equal to 2. So finally the distance between these two can be found out by subtracting 2 from the 3, which will give you 1. So we can conclude the inner radius small r is equal to 1. Whereas this is the outer radius of the disk, and from here you can say the outer radius is the distance of the curve from the axis of rotation, that is x equal to 3. For better understanding, let's take a picture without any kind of shade such that it will be easier for you to understand how the radius will be calculated and finally the volume of the disk will be calculated. So here is a clear picture of the solid so generated. Here if we look at the outer radius of the disk, from the figure we can conclude the outer radius is actually distance of the curve from the axis of rotation. This is the outer radius of the disk. And as this is parallel to the x-axis, So we can conclude here distance between this point and x equal to 3 will be actually the difference of the x between the line and the point. And as this point is lying on this curve y is equal to e to the power x, so from the curve we will get x is equal to ln y. And this is a line which have x is equal to 3. So the final conclusions we can draw as the outer radius capital R is equal to 3 minus x. And what is the x? X is from the curve y is equal to e to the power x. As we have the x as ln y, so finally we can conclude outer radius of the disk is 3 minus ln y. Now first we are going to find out the area of disk, which you can denote by delta A. As this is a circular disk, so area can be written as pi into outer radius, that is capital R square, minus inner radius, that is small r square. Substituting all the values, finally we are going to get pi. Capital R we have 3 minus ln y, and small r we have 1 to the square. So at the end we will going to get this is as 9 minus 6 ln y plus ln y whole square. 1 square gives you minus 1. So the delta A we can write as pi into 9 minus 1 gives us 8 minus 6 ln y plus ln y whole square. And the volume of the disk is actually the area multiplied by the width. So volume of the disk we can write as delta V as delta A into delta Y. So here we just need to put the value of the delta A, which is going to gives us the volume as pi 8 minus 6 ln y plus ln y the whole square multiplied by delta y. And to get the volume of the entire solid, we have to integrate the volume of the disk from upper point to the lower point or from the lower point to upper point. Both gives us the same values. At the lower point, y is equal to 1, and at the upper point, y is equal to e square. So you can conclude y is varying from 1 to e square. So to find the volume of the entire solid, we need to integrate this delta V from 1 to e square. We can write the volume of the solid of rotation V is equal to integration of 1 to e square delta V. Now substitute the values of the delta V into it. Keep in mind, in integrations, delta have to be replaced by d, V. So it comes as pi into 8 minus 6 ln y plus ln y whole square dy. We can find the value of the integration after separating each of the terms. So v can be written as pi. We can take the constant terms outside as well. So pi 1 to e square 8 dy minus pi 1 to e square 6 ln y dy plus 1 to e square. Here there will also be a pi ln y the whole square. And also you can take out this 8 and 6 outside. So 8 pi, and you left only with 1 inside of this part, 1 into dy minus 6 pi integration of 1 to e square ln y plus dy plus pi 1 to e square ln y square dy. Now you have to calculate the values of all the integrations, and we're going to put it here. So better we found out the integrals separately such that it is going to be easier to understand. Now the first value we'll get is this part, integration of 1 to e square 1 dy. After integrating, 1 become the y. So it is 1 to e square, which finally gives us e square minus 1. So this is the value of the first integral. Next is for the second integral, that is 1 to e square ln y. 1 to e square ln y dy. Ln y actually cannot be integrated directly. So here you have to use the by parts. But to use the by parts, we need to have two different variables for by parts. So we can write this integration as 1 to e square 1 into ln y dy. Now you have to apply integration by parts into this 1 into ln y. So let's start by taking a look at the integration by parts formula. Here, if u and v are two function of the x, or any one of them can be constant terms also. By using by parts, you can write integration of u into v as u into integration of v dx minus integration for the whole expression of du by dx into integration of v dx. As we need to integrate the v, so v should be a term which will be easily integrable. Now, if we look at the expressions we are trying to integrate, y into ln y, integration of ln y is not known, but integration of 1 we can take as y. So if we apply the integration by parts into this expression, then it will going to give us equal to ln y into integration of 1 dy minus integration of differentiation of ln y into integration of 1 dy, the whole integration for better understanding, we will keep the limit outside this, the entire part, the 1 to e square. Now simply integrate it. ln y, integration of 1 will give us y minus, inside this integral, differentiation of ln y, that is 1 by y, and integration of 1, that is y, dy of it, which is 1 to e square. Finally, we are going to get this is as y into ln y minus, as this 2y getting cancelled, we left with only 1, and integration of 1 is y. So 1 to e square. So now you have to substitute the upper limit and the lower limit in the integral. So if we substitute the value of the upper limit, that is e square here, it will give us e square ln e square minus again e square, and for the lower limit this is ln 1 minus 1. Here you can use two value. First is ln e square can be written as 2 ln e, and ln e is 1, so finally we will get 2. And if we look at the ln 1, the ln 1 is 0. So finally we will get this is equal to 2 e square minus e square plus 1, and the conclusions comes as e square plus 1, and this is the value of this integral, 1 to e square ln y. Fine. Now we left with the third integral, that is ln of y square. Here also we have to use the integration by parts. For that we need to take it as 1 into ln y whole square dy. We are going to take this as u and this is as v, because of the same reason that y is easily integrable. So finally it gives us ln y square into integration of 1 dy minus integration of differentiation of ln y square into integration of 1 dy. And we have to take the limits for the entire expressions, 1 to e square. So now we are going to split the limit for both part. First part become y into ln whole square. The limit is for 1 to e square. And in the second part, both the y is getting cancelled to gives us integration of 1 to e square to ln y dy. In the first part, we can substitute the upper limit and lower limit, which finally gives e square, and here it is ln e square the whole square minus 1 into ln 1 the whole square. From this we can take out 2, and which left us with integration 1 to e square ln y dy. We already found out in the last integral the ln y e square is equal to 2. So this expression gives you 2 square, that is 4, which become 4 e square. Whereas if we look at this ln 1, we already found out 0. So this expression become 0 minus 2 into From the previous part, we already found out the integral of 1 to e squared ln y dy we have is equal to e squared plus 1. And we're going to substitute these values in the current integral. So after substitutions, the current integral become 2 into e square plus 1. So if we open all the brackets, this become 4e squared minus 2e squared minus 2, which gives us 2e squared minus 2. Now we are going to substitute all these values of the integral into this expression. After substituting all values into the equation 1, we'll get the volume V is equal to 8 pi into e square minus 1 minus 6 pi into e square plus 1 plus pi into 2e square minus 2. Now we need to simply calculate all of them, like 8 pi e square minus 6 pi e square plus 2 pi e square gives us 4 pi e square, whereas minus 8 pi minus 6 pi minus 2 pi gives us 16 pi, which in other words can be written as 4 pi into e square minus 4. So finally we can conclude the volume of solid is equal to 4 pi into e square minus 4. That's all. Hope you understood the procedure to find out the volume of the solid so generated. In the next video, we're going to rotate the resin about a line parallel to the x-axis. Till then, goodbye. Have a nice day.